Hello students, welcome to Lucky Learning. Here in this video, we are going to discuss one of the important concept of memory organization, that is cache memory and its mapping processors. We know that CPU can access data from main memory. Means if any program that is to be executed, that program should first come into main memory. And between the main memory and CPU, if we place cache, and the access time of cache is very fast when compared with the main memory, so that execution speed can be increased. And what we store in the cache? In the cache, the total program need not to be stored. In the cache, we can store only active portions of the program can be stored into the cache. Active portions means most of the time the program spends inside a loops, nested loops, functions, and those are called active portions of the program. That active portions of the program, if it is placed in the cache, as we know that cache is more faster when compared with main memory. Let us say a typical example. If one instruction to access main memory, from main memory it takes 100 nanoseconds, but from cache memory it is 10 nanoseconds. It is a meaning that 10 times cache is faster than main memory. That is just typical example for understanding that numbers. It means cache is more faster when compared with main memory. What main memory contains? Active programs. How active programs are going to be bring into main memory? Because all the programs are available in the magnetic disk and magnetic tapes. These are auxiliary memory. Auxiliary memory contains inactive programs. Through IO processor, those inactive programs, when it is to be executed, it should be brought into main memory, so that those programs are called active programs. That active programs can read by the CPU and execute. But access time of main memory is more. To improve the speed of execution between the main memory and CPU, we placed cache memory. Cache is a faster memory when compared with main memory, so that execution time can be reduced. It means speed can be increased. Here, the speed of main memory is very low in comparison with speed of modern processors. Hence, it is important to devise a scheme that reduces the time needed to access the necessary information. The efficient solution is to use cache memory, which essentially makes the main memory appears to the processor to be faster than it really is. So it means the program appearing to the CPU is appeared as very faster, but really it is not. It is appearing to CPU as very faster because between main memory and CPU we have added cache memory, so that it appears to the CPU that program is available very fastly. Now look at what CPU will do. CPU is going to make a reference to main memory. CPU makes a reference to main memory for the first time. And a word from the main memory is to be read, and that word is to be sent to the CPU, and also that word is to be stored into the cache memory. Whenever CPU requires the same word next time, what CPU will do? Make a reference to the cache and access it for n number of times, so that access time becomes reduced, execution speed is increased. And suppose whenever CPU makes a reference to cache for some memory word, and that memory word is present in the cache, then we can call hit. Suppose if CPU make a reference to some word in the cache, and if the word is not present in the cache, then it is called miss. If a miss occurs, what CPU should do? Again, it has to brought that memory word from main memory, and parallelly it is to be stored into the cache, so that next time whenever CPU requires the same word, it has to take it from only cache, so that execution speed can be increased. Suppose if CPU make a reference to cache and word is found, hit. If it is not there, miss. If a miss occurs, CPU has to brought a word from main memory to CPU and also stored into the cache. It means it will take some extra time to get a memory word from the main memory if there is no hit. Then it is called miss penalty. Means it requires extra time to get a memory word from main memory to CPU. We call miss penalty. Suppose hit ratio is 95%. Obviously miss ratio is 0.05%. How to calculate the average access time? The average access time is hit ratio into access time for the cache and miss ratio into access time from the memory. Here, these are the simple definitions for you for your reading purpose. The purpose of cache memory is frequently measured in terms of quantity called hit ratio. When the CPU refers to word and finds it in cache, it is said to be a hit. Otherwise, it is a miss. So, hit ratio is calculated by number of hits divided by hits plus misses. Suppose if whenever hit not occurred, the extra time is needed to bring the desired information into the cache is called miss penalty. Now, the point is whenever a miss occurs, the memory word is to be brought from main memory and also copied into the cache. So means the word in the main memory is to be mapped with word in the cache memory. This is called a mapping process. Look at the transformation of data from main memory to cache memory. So means word in main memory is mapped to word in cache memory is referred to as mapping process. For mapping, we have three types called associative mapping, direct mapping, and set associative mapping. We'll discuss each of the technique in detailed way. First, we'll start with associative mapping. And before we start, we'll make some simple understandings of main memory and cache memory. With these numbers, we are going to understand those techniques. We know that CPU make a reference to main memory. Assuming we do have main memory of 32K words, each word is 12 bits. 32K is equals to 2 to the power of 15. It means it requires a 15-bit address. It requires a 15-bit address to address the main memory. And each word is how many bits? 12 bits. So each word is 12 bits, and like this we have 32K words. To address each word in the memory, it requires to use 15-bit address. And between main memory and CPU, we have a cache. As we know that cache is smaller in size when compared with main memory, and here I'm assuming cache of size 512 words. 512 means 2 power 9. It means to address the cache, we use 9-bit address to address the cache. And each word in the cache is of 12 bits. Now observe, the word in the memory is 12 bits. The word in the main cache is also 12 bits. What CPU will do? Make a reference to main memory. How? By sending a 15-bit address to the main memory. So what main memory will do? It responds with CPU by sending the 12-bit word. This is a memory word. That memory word is 12-bit word, and that 12-bit word is sent to the CPU, and also parallel it is to be stored into the cache as a 12-bit word. So it is a 12-bit word in the cache. So here the mapping of 12-bit word from main memory into cache is called mapping process. Is called mapping process. Here we should understand that CPU always make a reference to cache, because once word is available, it will make a reference to cache and read it continuously. So means CPU first sends how many bit address to cache? 15-bit address to cache. If there is a hit, the CPU accepts 12-bit data word If there is a miss, CPU reads the word from main memory and the word is then transferred to cache. Here, to understand it, instead of showing 15-bit address, we are going to represent this 15-bit address in octal form. Means 15-bit address of main memory I'm going to represent in the form of octal address. So in 15 bits in octal, octal uses 3 binary bits to be represented as one octal digits. So to address the main memory, we use 5-digit octal address. 5-digit octal address. And 12-bit word can be represented as 4-bit octal word. 4-digit I can say. 4-digit octal word. Here in the cache also, how many digit octal word? 4-digit octal word. And how many bits cache address? 9-bit address. 9-bit address means 9 you divide into 3 bits groups. So we can use 3-digit octal address for addressing the cache and 5-digit octal address for addressing the main memory, and we use 4-digit octal word to access word from the main memory as well as from the cache memory. So these things you do remember. First, we'll discuss about associative mapping. The fastest and most flexible cache organization uses associative memory. And we know that associative memory is also called content addressable memory. So it is to search based on the content. And the associative memory stores both the address as well as data of the memory words. It means if some word is to be transferred from main memory, suppose 01777 address location from the main memory, suppose it has some word 1234, and this is whenever it is to be mapped into the cache. What is to be stored into the cache? In the cache we have to store the address, that is 01777, along with the data 1234. Means what cache should store? The cache should store address as well as data. And it means it permits any location in cache to store any word from main memory. So address will have 15 bits, and this 15-bit address will be showing as 5-digit octal number, and its corresponding 12-bit word we are showing as 4-digit octal number. Now here you look at, suppose it is to store suppose it is to store this memory word 1234 memory word from main memory to cache. How it is to be stored? In the cache it will be storing the address as well as the data. See, address 12000 and data 1234. Next, whenever CPU requires this word, so what is to be stored? The address 70,000 and the data 3456. That is to be stored into the cache. Next, whenever CPU requires this 60,000 location data, so that it stores 60,000 address and this data into the cache. So that whenever CPU requires one of these words, it is to search based on that address. If address is matched, then corresponding word is to be read from the cache. Okay, it means what cache stores? Address plus data. Now here you look at how it is going to search. Whenever CPU requires some word, first CPU make a reference to cache by sending 15-bit address. We have represented 15-bit address as 5-digit octal number. Now this is a 5-digit octal number, is address is sent to the cache. Now this address is stored into the argument register. This register is called argument register. That argument register will store the address of main memory which is sent by the CPU. Now the value in this argument register is compared with address part of the cache memory. Wherever address part of the cache memory matches, the corresponding word is read out from the cache and it uses by the CPU. Now it is a simple techniques, but we know that the associative memory is costly. Associative memory is costly. And one more thing, what happens when cache is full? When cache is full means all words in the cache are occupied. Now that address data pair must be displaced to make a room for a pair that is needed and not presently in the cache. Suppose if it is required to store some word into the cache, and assuming cache is full, so what it will do, it will replace one of the cache word, assuming this word is to be replaced with another word. Suppose another word is in the location 12777 and the data is 1234, and if the cache is full, it will replace one of the cache word with another word from the memory. Fine. But the drawback with the associative mapping is associative memory is very costly. So we go with the next technique called direct map. Associative memory is expensive compared to RAM. So that we go with the alternative technique called direct mapping. Here in direct mapping, what we do here, assuming memory will take 2 power k words or 2 power n words for addressing the memory. Means n bit address we use for addressing the main memory. Okay, addressing the main memory. And k bit address will be used to address the cache. It means previously what we have done, we have stored the n bit address of memory along with the data into the cache, and where we have stored in the cache at any location in the cache wherever it is free. Now instead of storing the n bit address plus data, all 15 bits of address plus 12 bits of data into the cache at any location, so totally 27 bits we have stored into the cache word at any location. Instead of storing at random location, it can be stored in the location where the least significant of k bits that matches with the cache address. So in that location we have to store. It means in our example, cache uses 9-bit address, memory uses 15-bit address, and we use n-bit memory address is to be divided into two fields. Now k bits to address the cache, and we call it as index, and n minus k bits we call it as a tag. And in a cache memory, now we should not store the complete address. Instead, we should store the tag plus data. Now, look at what happens. What happens now? This 9 bits address we use to address the cache, 9-bit address to address the cache, and the remaining 6 bits to check whether that particular word belonging to the required memory address data. See, it means that suppose from main memory we are bringing this memory word. So this is a main memory word. Suppose main memory word is 1234 in the location 02777. It is an octal address. Now whenever miss occurs, this memory word is to be brought into the cache. In the associative mapping, what happened? We have stored this memory address 02777 along with data 1234. Totally we have stored. This is in the case of associative mapping, and where we have stored in the cache at some random location. Now when in the case of direct mapping, where we have to store this memory word is to be stored into the 777 location of the cache. It is stored into the 777 location of the cache. It means this is used as an index. Instead of storing it in random place, it is to be stored at index in particular location. What value we have to store? 1234. But we have used lower significant 9 bits or 3-digit octal address location. We have stored the data. But the data belonging to this particular location or not, we use most significant 6 bits or two most significant octal digits will be used as a tag. So it means now we have stored this memory word in 777 location we call index, and the data is 1234, and the most significant 6 bits are used as a tag. It means in direct mapping what we store in the cache, tag plus data. Now look at here, this is a memory data, main memory, and this is a cache memory where we have to store this memory word. This memory word is to be stored directly into the cache address of 000. Okay, it means this one. What is a memory word? 1220. And the most significant 6 bits or 2 octal most significant digits are used as a tag. Now you tell me where we can store this memory word 6710. 6710 is to be stored into the cache address of 777, and 6710 is stored, and along with what we have to store, the tag is 02. This is a way we have to store, right? Now once we store the memory words into the cache as tag plus data, whenever CPU requires, CPU makes a reference to cache. How CPU make a reference to cache? CPU sends 15-bit address, and that will be stored into the argument register, and we have divided address into index as well as tag. Now how it will search in the cache? Cache will be searched with index field. It means index is 500, it will go to the 500th location, and it readouts the cache word. The cache word now consisting of tag 00 and data, that is 0146. But is it the exact word what CPU requires is or not? We have to conclude by comparing with the tag fields. It means now tag of the argument register compared with tag of the word that is read from the cache. If both are matches, then it is called hit. If it is not matches, it is called miss. Now the point is, what happens when CPU make a reference to 10500? Now the tag is 10 and index is 500. How it is going to perform a search? It will go to the 500th location, and this memory word, this cache word is read, and the tag is 10, and here the tag that is 00. It means there is a no match. No match means it is a miss. If a miss occurs, what it should happen? Now the memory word of 10500 addressed location, whatever value is there, whatever the word is there, that is to be brought from the main memory and stored into the cache. In which location? In the 500th location. In the 500th location, already memory word is there, and that is to be replaced with a new memory word. That's it. So that whenever CPU requires 10500 word, it is to refer directly from the cache and makes a hit. Now the point is, what you observe in two examples, these two memory words has the same index, but tags are different. Here for this we have a tag 00, for this we have a tag 10. It means memory words with same index but different tags cannot be stored into the same location. More than one cannot be stored. To avoid this problem, we go with a third method called set associative mapping. So we'll discuss here. The disadvantage of direct mapping is that two words with the same index in their address but with different tag values cannot reside in the cache memory at the same time. So that what we have to do, instead of storing one word, we have to store more than one word. Let us say tag 1, data 1. Again, if one more word with same index is there, so but different tags, that also to be stored in the same cache word as tag 2 and data 2. It means what we have to store in the cache word, in the cache, in one word we have to store more than one word of the memory, that has same index but different tags that forms a set that is called set associative mapping. Now look at each data word in the cache is stored together with its tag and the data, and that is called tag data items in one word cache is said to form a set. Means more than one word of memory is stored into one word of cache is called set of memory words can be stored into one word of cache is called set associative mapping. Here you look at where we have to store this value. Let us say an example of 0 1 0 0 0, this 3450, where it is to be stored in the index of 000 of cache. What we have to store 3450 data along with what is the tag now 01. And suppose if it is to store this memory word, where is to store in the index of 000. In the index of 000 already one tag data pair is there. And what we can store one more data word 5670 but different tag 02. So it means in one cache word, how many memory words we have stored? 1 and 2. Two memory words we have stored, so that we call it is a two-way set associative mapping cache. Same thing you can observe 0 to 777, where we have to store, it is to be stored into the index of 777. The data word is 6710 and the tag is 02. And look at the same thing 00777. This is a 2340 word where it is stored in the index of 777 and with a tag of 00. It means each cache word is storing two memory words. That's why we can call it is a two-way set associative mapping cache. And this is can be extended to k-way set associative. Means k memory words can be stored one together in a cache word. Now look at each index address refers to two data words and their associated tags. Each tag requires how many bits? 6 bits, and data uses 12 bits. It means one memory word will be stored as 6 plus 12, 18 bits. In one word of cache, how many memory words are stored? Two words. It means one word of cache will have 36 bits. And we have cache of 512 words. And each word will take 36 bits. It means two words in the memory. So 512 words, each word will take two words of memory. It means how many words of memory can be accommodated by the cache? 1024 words of main memory can be accommodated by the cache, so that hit ratio can be increased. In general, set associative cache of set size k. Previously we discussed 2, now I can say k. It means one word of cache can store k words of main memory. And whenever CPU generates a memory request, the index value of the address is used to access the cache, and the tag field of the CPU address is then compared with all the tag fields to determine whether the match occurs or not. So means whether hit occurs or not. If a one word of cache stores more than one word of memory, ultimately hit ratio is going to be improved. Now look at, this is a two-way set associative cache. What CPU will do? Sends an CPU memory address, and that memory address is stored into the argument register. And memory addresses, now we have two parts, index as well as tag. Now index is 500. Now what it will do? It will go to the 500th location in the cache, and it reads out the tag 1 00 and its data, and also tag 2 and also its data. Now two words of memory is read from the cache. Now among the two words, which word is required by the CPU? That is to be verified by comparing with the tag. Now this tag which is sent by the CPU is compared with the tag 1 and also compared with tag 2. And there is a possibility of a match or no match. Suppose if a match, we call hit. If there is a no match, we call miss. If a hit occurs, it is going to read out this memory word from the cache. Now the point is, because at each word in the cache we are storing more than one words of the memory, so that ultimately hit ratio is going to be increased. Now the point is, suppose we are going to access, our CPU is going to access from index 500, but the tag is 20. What it will do, it will go to the 500th location, and this tag and data words are read, and but this 20 tag is not matching with tag 1 and not with tag 2, then it is a called miss, because there is no match. If a miss occurs, what is to be done? One of the tag data pair is going to be replaced with new data word. Suppose in the memory 2500 location, in the main memory we have some data 1 2 3 4. So that what it will be done, so go to the 500th location in the cache, in this location, and because a miss occurs, one of these tag data pair can be replaced with this new words. What is a new word? Suppose 1 2 3 4, and the tag is 20, that is going to be replaced. So which tag data pair is to be replaced, it is going to be decided based on the page replacement algorithms. As we know that when a miss occurs in a set associative cache and the set is full, it is necessary to replace one of the tag data items with a new value. For associative and set associative cache, which location should be emptied when the cache is full and a miss occurs is decided based on the page replacement algorithms. We have first in, first out, least recently used, least frequently used, random algorithms. These algorithms will decide which tag data word is to be replaced in the cache. This is decided by the replacement algorithms. And these are the three mapping techniques, and how these three mapping techniques will work with the CPU, that we have understood. Hope you have understood the concept very clearly. If you like the video, please do like, share and subscribe, and don't forget to click on the bell icon for the regular updates. Thank you.